Okay, we're going. Okay, guys, my last live stream, should I say, has caused people to have lots and lots of questions about detector coils, self-resonant frequencies. Will particular coils stop working with modified detectors and stuff like that? It depends how highly modified the detector is and how fast you clock the detector. And also, it depends on speed of decay signals as well, to a degree. And this is where high self-resonant frequency is usually indicating it's better for detecting very, very small gold or very fast decay targets anyway. So anyway, what we got here, I've got this, this is a coil I built. It's an experimental one. As you can see, it's got really thick cable on it. It's got the extra ground wire running down it. And what I've done, I'll tell you what I've done. This is the best way to compare coil against coil. Not for anything else, but just checking the self-resonant frequency. Basically, you got to check everything else out. The inductance of the coil, series resistance. How much power you can, DC power you can get through the coil, because you don't want that to be high. You want it to be low, within reason. You want it to be around about, I don't know, 0.2 to 0.4 of an ohm, something like that. Can go higher, but something of that nature. 250 to 320 microhenries for your coil. But anyway, you can mathematically work all this out. It's basically it's pretty straightforward. Now, the way I do it, you can do it with a resistor, but it gives a very broad frequency response. Now, I'll show you what I'm doing. I'll bring this over and I'll point it out down there. I have to undo that to do this. Okay, there, that thing there is a very high quality mica capacitor. It doesn't have to be, but I'm being pedantic and using a very high quality 2% mica capacitor that actually is manufactured. It was manufactured in the Ukraine for HF radios. But yeah, it is a mica capacitor. Whoopsie, there's me clipping the side of the tripod with the chair. Chairs with wheels and outrigging legs. It's a real worry. So anyway, that's it there. That's just in series. The capacitor is in series with one wire of the coil, and I'm on the coil lead, and I've got the oscilloscope connected across the capacitor. So I've done it in the return leg. Makes it easy. It gets rid of a lot of stray parasitic capacitance. So let's have a look here. I'll try and get both of these in frame. Now I can't move in because I moved the tripod really close. Hang on. I'm just going to remove a 7000 out of my way. They can go over there without bumping anything. Now, if I touch the coil, you see there's no movement on the oscilloscope. It's not going to do anything. I think if I actually put my hand across it like that, it will. No, it doesn't. Okay, it's very, very stable. There's metal objects kicking around. It doesn't care less about it, right? It's not going to change its self-resonant frequency too much. Not that we can even notice. So this is very rough as guts, but it'll give you a really sharp indication. It doesn't give you the actual indication because I have an added capacitor in series, which will change the self-resonant frequency of the coil. It will actually lower the self-resonant frequency, but we're going to be testing coils against coils with the same test infrastructure. So it'll just indicate this coil's better than that coil or worse than that coil or whatever. The faster the coil, usually the better they are. That's in my own opinion and my own humble experience. So what are we sitting at the moment? We've got the signal generator sitting at 61.8 kilohertz. Not that it means anything. And I'm not showing the, I'm using a sine wave. Don't have to show it. Just look at the, because it goes all jittery if I'm trying to show a waveform, and it it has a argument with the refresh rate of the oscilloscope and the scan rate of the iPhone camera. So to alleviate that, I just make it a big block of whatever it is. So anyway, let's take this thing up and we'll see where we peak in frequency. So we're at 69, up we go, it's getting bigger, up to 162, it's going to do big jumps here. Okay, we're getting near the end. Oh, I might have to rescale it. Oh no. Yep, hang on, I've got to drop the power level out the generator. I'll just drop the power level like that. Go back to frequency. Now I'll try and peak it. This thing's very jumpy sometimes. Yeah, it's at the crossover point. That's right. There it is there. 203 kilohertz. So it's not saying the resonant frequency of the detector coil is that, but with the capacitor in series, that is our indication of peaking at 203 kilohertz. Now, what we'll do, we'll try a smaller coil around about, you also got to check the inductance of the coils too. If the inductance is all over the shop, you're going to get different frequencies as well. But there is a formula to calculate all this out. So you can measure the inductance, write it down. You can see where your fixture is, capacitance-wise, write it down, and then we can go and do the old, mathematics and use Mr. Pi in the equation and work out the LC ratio. We can work out and compensate for the other capacitor, and we can then compensate the whole structure here, and then work out the real self-resonant frequency of the coil. If it means anything to you, yes, we can do that, but we're just going to compare apples with apples. Well, as one would say, something like that. So we'll put this bit down again. So that was 203. I've got this sitting device. I'll pop that out. Okay, we'll get rid of that coil. Oops. I'm really squashed in here with the tripod. So what we'll do, we'll use this 8-inch Minelab mono from years ago. I don't think it has seen much work, but who knows? We'll have a look. Probably won't make, it's not going to make much difference anyway. So I'll just tighten that up, and I don't want anything to fall off. That's the main thing here. I want to get that into the inner connection. So I've cleaned that up. I should have used a socket, would have been better. Coil socket rather than poking wires in it. But anyway, this will work. Okay, this is the 8-inch. We'll see what happens. Okay, 215 kilohertz. Now, is that the way it's wound, or is it just small? And being small, it's more reactive. Look at that. It was wiggling around there for a bit. Now it's not. Hang on. Let's pick it up and just see what's going on. Oh, if I squeeze, oh, I'm squeezing it. Yeah. Okay. It's got a bit of movement there. It's probably might be the carbon on the paper in there, or the cardboard. That it's a little bit so-so. So we've got that. Okay. Now that's showing higher, but I know the when I measured the inductance of this coil, this was lower. My one I made over there, I think it's around about 325 microhenries. That'll explain that why it's a tad lower. So if we had the coils that are all exactly the same in inductance, then we can actually just easily direct compare. But because the inductance changes per different coil, it has to be compensated later on. So I'll get that, we'll try that. Now what I'll do, now you got to remember, these are very old, that's very old coil. How about we use a commander coil, which is the factory standard one. So we'll use a 11 commander and stick it on there. We'll see where it lands. The inductance of these coils with the smaller one are usually near enough, pretty close to being exactly the same, within about 5 microhenries. So not like mine, which is off the reservation a little bit because it's very high. I'll stick that in there, and I'll stick that in there. We'll see where we go. Should have wound the frequency back, but we might be in the same ballpark. We'll have a look. Okay, 210 kilohertz. So what you make of that is what you make of that. There we go. 210, 212, somewhere around there. But it's not the actual self-resonant frequency because of that capacitor I have in series. You've got to remember that. I need to measure the voltage drop over something else. I don't know what's going on. So I'm using a capacitor. You can use a resistor, but with a capacitor, you get a very, very sharp, defined peak. Now, if you want to see what happens when you go past the resonant frequency of a detector, say you had very fast decaying signals, tiny little bits of, gold giving off very fast decay signals, what would happen? And if they're above the self-resonant frequency of the coil, well, tell me the decay speed of gold. You'd have to go and measure it, but depends on the target, the size of the target, the surface irregularities, the actual purity, the coatings, everything will affect the skin effect on metal, and it will give you very, very arbitrary all over the shop readings. So we'll have a look at this now. If I go, look at this, I'm just up to 215 kilohertz, 222, and at 382 kilohertz, we're actually cactus. We're dead in the water. You're not going to get a signal out of that if the decay rate is above the self-resonant frequency on this coil. If we take it to the self-resonant frequency, which I just shot past because this thing is jumping from kilohertz to megahertz because I'm turning it too fast, it does that. It does automatic transition. Depending how fast you turn the knob, you can go in, turn it really slow, it'll be doing hertz, tens of hertz, hundreds, thousands, and then you turn it a little bit faster and it goes, oh, I'm going to do 1 megahertz jump. So it's just so you can get up anywhere on the frequency range really quickly rather than just twirling it around, or you can go and key it in on the keypad, of course. But let's have a look. We're at 209 kilohertz, and if we look, we go down, and again we get away from the resonant frequency, and there you can see the actual sine wave I'm sticking in there. But if I got rid of that capacitor and directly connected this to the coil, we can get the same sort of result, but it won't be as pronounced. We should run a resistor in series, but oh, look, it's really quick and easy just for me to jump that there and get that on there. Okay, you won't see anything at the moment. I've got to crank the grunt up on the generator, and we are directly connected. No, we're not. No, because I've got to put the oscilloscope on the other side. You're not going to see anything. That would help. Okay, I'll put it there. Okay, in, ground. There we go. We should be able to get something out of it. So I'll crank the voltage up. Get a 10 volts. So I'm sticking. It's getting loaded down, of course, but I'm putting 10 volts into this, and Let's see if we can crank this scale down. We're not going to worry too much about the pattern, but we'll just see what a direct connection will do for the self-resonant frequency of this coil. And look at that, up it goes. So at 1570, I'm going to have to change scale again. Oh, I'll actually just drop the power down. 10 volts is a bit too grunty. Try it there. Back on frequency. Now you remember we were getting peaks. I'm going to go down, even drop it even more. Try amplitude. I'll drop it to there. We'll see how we go. Back to frequency. We're at 5 kilohertz. It's going to go a lot higher than that. Okay, we'll drop it down again. I could do it on the oscilloscope, but no, I'll see how we go. Still going up. We just hit a jump point there. 26. I've gone from putting a volt into it down to 1 volt. We'll put down to near half a volt into it or something of that nature. We're at 33 kilohertz. Okay. So it's hard. It's right in the middle of the range where it's going to. It changes the oscillator in the generator. It's a pain in the proverbial, of course. And see, if on a direct connect, where are we? About, yeah, that's amazing. 1.6 megahertz odd. And then if we go past that, if anything decays really fast, it's gone. I don't think we're going to have things decaying at 18.5 megahertz, but you get an idea that anything that is above the self-resonance of this coil, you basically start getting a reduced return signal from that. It basically is less. The faster the decay, the less. So you really want to go for a very high self-resonant frequency, somewhere around there. Oh, sorry, what am I reading? Oh, I thought I was in megahertz range. No, I'm not. Sorry, it's 161 kilohertz. Helps if I read things properly, doesn't it? 161 kilohertz. So that's definitely, I would say, not the way to read a coil. You need a resistor or a capacitor, and you've got to take those into the equation. But yeah, obviously the port, or actually I'm on sine, aren't I? And hitting in direct like that, I should be running a square wave. Yep. It's funny, really, you're meant to be running a sine wave, but it's funny when you think about it that you're hitting these coils with a square wave in real life. There we go. So doing it properly, should use a sine wave because all the mathematics is based on sine wave calculations. So that is that. That's how you should be able to measure the self-resonant frequency of a coil. Instead of using the capacitor, how about I do one? I'll just use a resistor in there. I need to connect. Moved all the wires around. There's another way you can do this too, you know. It's using the Hall effect devices I got. They're fast enough to do this. Where's that resistor? I had a resistor there somewhere. I think the resistors. See, everything on my bench takes a walk. Where are you? Now it's disappeared. Funny about that. Now I'll go back to the capacitor then. Because we can calculate the value of the capacitor. So there we go. Whack. Too much voltage into it. Back to frequency. Oh, do it there. It's quicker. Yeah, 212. I wonder if I got some other coils around the place that I can actually do. How about, what have I got? I got drawers of coils, but a lot of them I don't want to drag out. Yeah. Can't find anything. But while I was looking in the drawer, I did find that if you want to make up coils with power for dongles, that's a mono cable. You can, make coils up, chop the plug off or whatever, and make your own dongle, and use that down to the coil for whatever reason. You can just use mono cable, but we have that. So yeah, that's well, if you ever wrecked your 6000 cable, for instance, you could fix it with that, because that's the same stuff. I'll just let you know what we got kicking around. I think it's some 7000 cable somewhere too, but where is it? Don't know. That's SDC 2300 cable. Hang on. Here's a coil. I'll throw that back in. Yeah, this will work. I want to see what the self-resonant frequency of this is. Oh, actually, because they're all tangled up with their leads now, they're all going to come out. Okay. I've got this coil here, which is a hard shell coil. It's one David made. So I'll just disconnect all this here, and we'll see how this stacks up. Rather than just measuring the self-resonance of the coil, we should also probably be taking into account everything all together, and you'll probably end up being a very complicated mathematical equation to work out the overall loss tangent of the coil. Anyway, let's see this thing. We'll get this, and I'll stick that in there, and that one in there. Excuse my fingers touching the oscilloscope lead. I've used very fine wire. I shouldn't have done that. Hard to get into You can get in there. Okay, this is one of our coils. Let's have a look. Peak. Okay, 210 kilohertz. Like I say, this isn't a specifically made high Q coil, but put my hand in certain spots, it's going to change for some reason. Oh no, I'm wiggling the cable. Stop wiggling. There we go. That's better. So yeah, they're relatively all ballpark figures, but we do need to work out the inductance of each coil. Otherwise, that'll throw the it completely skew the results if you don't compensate for that. So I think I was looking at the formula for that. Just moving coils around the place. You know, I had the formula for that somewhere. Where is it? So if we want to work it out, it's 1 over 2 times pi times the square root of L times C. So that's if you want to work out the inductance of the coil. But I can just measure it with an inductance meter, so it makes it a lot easier. I think we can compensate it from there if need be. But yeah, it's interesting when you do it this way, because it's showing that most of the coils are all within the same ballpark figure. What I will do, I will try a very high Q coil. Well, I know it's a high Q coil. Oh, damn it. I really... How am I going to do that? Hang on a second. I can't do that because it's it'll be exposed. Oh no, I can do this. This is a funny little coil. Okay, this is bang on 300 microhenries. Okay, this is it's not shielded. It's actually for making very small coils, just a former. So that's it. It's just a small one. We'll have a look and see what goes with this. It's got no shielding on it, so, but we're not using it to look at signals, so it's no big deal. In it goes, in there. Let's have a look. Get in there. I really should have made a socket up. Murphy's Law. You're going in the vise now. Yeah, no escaping the vise. Because what do you think happened? It fell on the floor. It slipped down. Okay. Took all the wires with it. Okay. Get in there. Okay, we're in there. Hooray. So this little coil here. Oh, God, stop jumping around like that. I can already tell that that has less losses. There's actually more amplitude in that. It's probably because it's got no shielding on it, chewing up the power. Anyway, that's 211 kilohertz. Basically, how that's connected up. So you can touch it. It'll. I'm just touching the coil connection wires, and that just kills it. I'll lick my fingers and do it. There you go. That's why you don't want water getting in your coils. Okay. Yeah, look at that. That's just wet fingers touching the coil connections. Crashes it big time. So well, it's basically got a capacitor in series it's going to, isn't it? But yeah, when we start looking at the way these detectors work, what it really is, that if you're worried about your detector going deaf with particular coils which are of a little bit higher capacitance. The only mode I've ever found it to affect really is definitely on the 5000s. It absolutely will start affecting the fine gold mode. If it's bad enough, it'll affect enhance. And normal mode doesn't give a rat's about it, doesn't care less. It is just very, very forgiving. But the other ones where they're using very fine pulses and that, very fine time windows, very quick time windows, if there's any residual signal from high capacitance in your coil, well, it dags around, gets in there, and it's basically above the signal level, and the detector thinks it's getting swamped by a lot of signal, and it just desensitizes. It can't reset. Now I've got coils all over the floor. So, you know, trying to think if I've got coils out in the garage, but yeah. Well, actually, what we should do, how about we look at a proper double D coil? I think this might be of interest. So here's a fairly new double D. Because you remember the double D windings there? Interesting to say the least, but they do work. Okay, now which way are we around? If I get around the wrong way, I'll be on the receive windings. I want to be on the transmit windings. I think it's that one. That one. Soon find out if I'm wrong. Won't work very well. Okay, that might be on the receive winding, I think. Let's have a look. Yeah. Yep, that's on the receive winding, right? That's what I mean about the double D coils. Self-resonant frequency on that setup, just on the receive winding, is 130 kilohertz. It's nearly half of what you want, because the windings are all smothered in some sort of varnish. They're very, very fine, so there will be overall some resistive loss in there, and also probably doesn't like being in close proximity to the transmit winding, but usually they run a little bucking coil to get around that, so there's not much interaction. So yeah, I've never done that with a double D coil. You're seeing it just the same time I've ever done it right now, and that is really, really low. That's really low. I don't know how double Ds work on very small gold. When you look at that, because you look at that, I haven't changed the amplitude of anything. Obviously, the amplitude should be higher. Sorry, but let's go up in frequency, and the whole thing just falls over. It just goes down to nothing. There you go. There's a double D for you. Now I'll get this around the right way. I'm working upside down, so obviously I got that around the right. This is a transmit winding. And I'll put it on there. I know they're bridged, but I'll just do it there anyway, internally. So we'll just wind this up and we'll see how the transmit winding looks, one of these. We'll get there. I'm trying to peak it. See, even the transmit winding peaking it's 203 kilohertz, so it is less than all the other coils we've tested. And maybe that is just the configuration of squashing the poor old coil out of shape. It affects the coil, and yeah, the self-resonant frequency drops. But yeah, I'm really surprised on the receive coil. Yeah, it was really well down in self-resonant frequency and also in amplitude. So Yeah, I didn't expect that. I mean, we haven't got a big load on it. We're just going through a 1500 picofarad capacitor. Anyway, it is what it is. So obviously the double D works by probably by the grace of God and just getting away from the noisy ground. Just getting that side of the coil, away from the noisy ground, and you get a better signal to noise ratio because it hasn't got ground decay tied up in it. Oh, as much as anyway. It's still in proximity, but yeah, that's interesting, isn't it? So, in my humble opinion, double D coil should be completely redesigned from how that's done, and I would be, in all honesty, I would wind the damn receive coil the same as the transmit winding, more or less. Not as heavy and hard as, but I would definitely space, do more air spacing on the wires in the wind, because you can tell that's just not very good compared to everything else we've tested. Well, I'm gonna put this one forward. People say, "Oh, double Ds are quieter." Yeah, they're quieter. Maybe they're just deaf. So maybe they're just totally deaf. So they're quieter, but because they're quiet, you can hear little signals. Oh, dear me. Has anyone ever done this and gone out and physically proved it one way or the other? Get a double D and wind the receive winding with half mil stranded Blitz wire. I don't mean half millimeter, I mean. Strand thickness, I mean the total bundle. Maybe make it something like 30 or 40 strands of 0.125 millimeter enamel copper. Make a big long length, stick it in your rotary drill, tie it to something, give it a twist. So you get a bit of it holds together a little bit of a twist. No, don't worry about that. I was going to say you could probably build up the insulation on it too, and then wind it. And it would be, I tell you what, it'd work a lot better than what I'm seeing here, for sure. 100%. That's just a no-brainer. It really is a no-brainer. So you can make a really good coil by doing it that way. Now you're going to see all the manufacturers make really good double D coils again. Remember one time, years and years ago, I said about there's a big market for very, very big double D coils, and out come all these big double D coils. So now we're going to see 00 winds or thick wind double Ds hit the market, aren't we? It wouldn't surprise me. Nothing surprises me. It's like you've got to give everyone the hint, and then they go into the manufacturing process. Yeah, so, yep. In my humble opinion, this is my humble opinion, double D coils, right, could be made to work a hell of a lot better than what they are. And as a prospecting coil, really, no joke, as a prospecting coil, and it's going to behave like that, I wouldn't use it. That's just woeful. I'd bin it. It's just, or rip it apart and rewind it. I don't like that at all. It's really, really woeful. There you go. There's a Q. Well, it's not really the Q. Well, it is, I suppose, but a sort of a loaded Q. And then we just take this here, and I'll go to the double D receive winding, and there you go. Well, you'll get the inverse on receive than what the power going in. So she's down, I don't know, probably losing 6 to 9 decibels of signal there. That's a hell of a lot. What's going on? My God. Or is it because the receive cable's really, really thin and high capacitance? I don't think so. It's not as thick as a transmit one, but the ratio should be the same in the spacing. So yeah, if anyone knows what's going on there, if you've got a different opinion than mine, go for it. I don't care. It just it's seeing's believing. It's obvious. There it is. We'll call that a bit of a dunger. I don't like that. So there you go. You learned something about double D coils. They are not very, very good. And that probably is for all of them. in general, because I think the construction is much the same, unless they're the manufacturers out there who want to educate us all and tell us that they make thick winding receive windings on their double Ds. Apart from that, I don't know. No idea. Okay. Oh God, I've got some. Actually, I'm going to have a bit of fun. How about we're going to look at the self-resonant frequency of a GPZ-7000 coil. I've got 6000 coil as well, but I don't want to do that because it's got the pain, the proverbial dongle in the coil, and you don't want to hook up something and do something wrong and pop the EEPROM or something, because it'll crack it. So while I'm here, come here you. I got this beast of a thing. Yeah, that was a donation from you know who. You know who you are. And because it was a donation, because I needed a dongle, so David made a GPZ-7000 plug dongle, so you can run any coil within reason on your 7000 as long as the configuration is right. I'm going to start making up some really good 7000 coils, and yeah, then you stick that on the end of it. just a standard. You know these you know, SD, GP, GPX connectors, everyone thinks that's what they are. They're actually microphone connectors. They've been around since about the 1960s. So yeah, they're made for microphones, just so you know. CB radio connector, CB radio microphone connector, which were pressed into use to make metal detector coils. Still work. There's still a big hunk of metal in the cable. You don't want big hunks of metal there. They sit there and generate their own field around them when they get energized. So if they take time to decay, guess what happens? Has anyone ever thought of that? That you put these pieces of metal, as in the connectors, obviously it's going to get whacked by the pulse, and yeah, if it doesn't decay fast enough, what happens? It'll sit there and generate eddy currents. So, you know, what I thought in the early days was it'd be great if you didn't have connectors onto your detector and you could just solder the coil wire directly to the circuit board with very, very thin soldering techniques. Yeah, get rid of all that metallic mass. I've proven it before. If you get a detector, here we go, trade secrets. If you get a detector and you clean up inside, and you say, oh, well, I'm going to go and resolder all the coil connectors and resolder some of the wires down to the board, and you go and put a ton of solder there, right? The actual performance of that detector drops off. I have found that out. And when you chop things away a little bit, thin them out, make sure that I'll tell you something. At one point, I found detectors that the receive wires from the coil connector to the board, they should have been tin plated copper stranded wire. They weren't. They were just pure copper. They were copper, and it was acting as a big piece of copper because there was no separation, or was no resistive separation between strands. So yeah, that was an interesting one. I can't even remember what detector it was, but it must have run out of wire sometime in the far distant past, and just went down to the local Dick Smith or Jcar store and bought some hookup wire because it was pure copper. You know, nah, don't do that. So no, I've discovered stuff like that, you know, in the past. I'm not saying it happens now. It doesn't. I think everyone's well aware of that sort of stuff, but you know, it is what it is. Okay, so I've got this. Yeah, so that's a nice little dongle. allows you to run any coil you want to design on a 7000, get around that dongle problem. Doesn't do anything else. Just tells the detector, you don't have a proper proprietary coil on it, so please don't work. So you make it work. That's what you do. So anyway, hang on, I've just got to get my meter out here because I don't want to stick this on the, well, I could stick it on the receive wires, but I want to go on the transmit wires. I'll just do it. I'll turn this one on. There we go. I'll look at the low resistance. So those leads are buried. Hang on, bugger that. Turn that on. I'll stick it on 200 ohms. It'll do. I'm only just trying to. I just can't remember which wires in the plug are which off the top of my head. You tell me which ones are which. So we'll just have a look. See. I hope this meter's working. It's just telling me everything's open circuit. Hang on. We'll go into buzz range, beep beep range. Hang on a sec. Okay. Well, that's basically 001. Not that it really is. So it's those two there. Is our transmit. These must be receive up here. Oh, come on. Where's the receive wires? Oh, there they are. 2 ohms. Okay, we're going to have a look at this anyway. I just want to have a look and just see. I'm going to transmit winding. Just have a look and see what it says. I'll probably have to hold this in my hands because the cable's a bit all over the shop. Okay, 7000 coil. Let's give it a crank and see what happens. $202 kilohertz with that circuit. It's basically the same as a standard Minelab detector. It's probably 300 microhenries. To me, it looks like it is. Well, it's actually reading the same as that transmit coil in the double D, because these coils aren't round. Remember, the transmit coils in these are rectangular. Maybe that drops the resonant frequency. I don't know if it would do it that much, but it would have an effect because a round coil is the most efficient coil, and as soon as you start doing elongations and weird shapes on coils, it does have a effect on its overall efficiency, in my opinion. In other words, it doesn't work. It doesn't work as good as a standard coil. Okay, guess what I've got here? I've got that Xcoil here. How did I try that? Where are you? It's in bits, of course, but I can get onto the transmit windings. It won't be fair because we haven't got the braided cable down onto it. But we'll just try it anyway. We'll see what happens. It's just this Xcoil, but I'll go on the transmit windings. I'll tell you what I'll do. I'll make a little transmission line up. I'll make a transmission line up out of two crocodile leads, right? So I'll twist them together and make a transmission line. So rough as guts. My God, this is as rough as guts. But oh, dear me. Let's have a look. Let's have a look anyway. Okay, clip one on there. Get on there. Clip one on there. Come on, work. Fire up. Okay, this is the Xcoil. But it's not fair. It doesn't have the lead on it, which would add capacitance. Well, actually add parallel capacitance. So let's have a look. It should be higher because of the way we haven't got the cable connected to it properly. Okay, there's your peak there, 207 kilohertz. I know these are I actually measured this, I think it was 300 microhenries, and it was the same, roughly around about the same resistance, give or take 0.002 of an ohm to a standard MyLab coil. So the center coil there is basically 1 millimeter square of copper. In how many strands they use, I haven't measured, but let's have a look at one of the receive coils on this. Now this will be interesting because everyone tells me these coils have an edge. Where is the edge? I want to know where it is. I know Mr. Xcoils watches my videos, so I'm not taking the you know what or whatever. But as you can see, straight away on one of those resin-filled double D type oblique structures, right? When's a coil not a proper coil? When it's squashed. Okay, but we'll have a look here and we'll see. Oh, look at this. This is interesting. Ah, now why? Now I'm gonna do the old Professor Julius Sumner Miller statement. I'm going to say it in the same voice if I can. Why is it so? Look at that. It's got a very, this is interesting. Okay, I'll tell you why it's interesting. It's got a very, very high self-resonant frequency. And I'll show you. This is interesting. Okay. 254 kilohertz. Ah, I know why. I know why. I'm a clown. Yeah, I can be because I just didn't realise that. I bet you these two coils are usually connected in series. I don't know that for sure. Actually, I've never measured it, and they're both 150 microhenries each, and that's what's going to cause a massively high self-resonant frequency because it's very low in inductance, and that will jack up the self-resonant frequency. Well, our sort of self-resonant frequency, because I still got this other series cap, and these will have a higher one again. There's the other coil there. Can I don't actually I've never ever looked at it, so I don't know. I don't know if, hang on a second. There's one way to find out, isn't there? Because we know how the basis of all these detectors work. So I'll get my LCR bridge meter, go and turn on. It's already on L. And I'll take that off there. The crocodile clip leads will make no difference to the inductance because they're nothing compared to anything close to anywhere near the windings or part thereof a winding. So we'll have a look and see what it tells us. 206 microhenries. 206. Now this doesn't make any mathematical sense to what I've been saying. So it's 206 or it's 412 if they're in series. So there's one, 206. Let's go on the other winding here. And should be the same. 207.7, or you got 0.5% error there. Better fix that. That's interesting, isn't it? So it's not a derivative of what we normally expect with these coils. That is now making me think about the other one, the other 7000 coil, which we dongled. Well, we took the dongle off, should I say? Hang on a second. I want to measure this. This is intriguing. So, okay, we've got some values here. We can actually utilize those and put them in our little black book for future reference. Okay. See, that's the MindLab normal coils, 297. But you know, I've got these leads in series, so we'll give or take a couple of microfarads. We aren't really, sorry, microhenries, not microfarads. Okay, and here you are. Here, there's your receive windings on the MindLab coil on that big GPZ-7000, and look what we got. Those coils, the receive coils, are in series. So we got, yeah, sorry, that's not right, is it? That's saying 39.15 henries. I thought it was going to say 391.5, but I'm off the reservation. Hang on. Come on, where's your winding? I had it there a while ago. Come on, click, click, click. There we go. Oh, that's better. See, it's ballpark 375.2. So, okay. I am intrigued. I want to know something. Hang on a second. I'm hooking this up directly on those receive windings in the GPZ. I'm trying to. All right, get in there. Oh, God, where are you? I've probably got it in the wrong connectors, have I? No, there it is. Oh, the damn wires are shortened together. Get in there. Here we go. Oh, let's have a look at this. Okay. Now, one of these coils peaked in that Z coil very, very high, but it wasn't the right inductance. Huh? Something's not right here. Oh, damn thing fell off again. Hang on a second. Let's see what's going on. Battery in the LCR bridge is going flat. Hang on, I was going to find those wires again. There they are, aren't they? There. Come on. Okay, there it is there. That connector and that connector. So why aren't we reading anything? Get in there. Yeah, I think the wires were touching. Okay, there we go. Well, what can I say? The self-resonant frequency on the MindLab coil, 185.2 kilohertz. And yeah. It's way down. I'm going to have to play with these a bit more. I think there's a lot that can be done with these coils. I really do. These 7000 type coils. I think there's something, I don't know, obviously they work, but anything will work. I mean, you know, you can make anything work, believe me. But how well it works is a very, very different story. But people tell me that these work better than those for a similar given size. I've got lots of research to do, people. I have a lot of research to do. I'm going to have to hook this up and make that series and try the Xcoil again. I've got some proper 7000 type cable. I can put that on and we'll see how we go with the measuring. So, yeah, that is rather bizarre, to say the least. So, yeah. So there's a bit of experimentation with coils. All the standard mono type coils, yeah, you could compare like with that, the way we did it. This stuff here we can't, not the 7000 coils, comparing against each other because this thing's pulled apart and it doesn't have proper cable connected. So what I might do is I might wire it back up and connect it. Another thing I'll do too, this coil here, as you can see, had two big ferrite tubes in here, and I've got them up there. So what I'll do, how about I make this coil, make it all proper again, how it's meant to operate, and then I will add the ferrite, and we'll do measurements with the ferrite there, and we'll do measurements without the ferrite there. Yeah, that was all shorting out in the oscilloscope, so I just knocked it on the floor. So that would be another experiment to do too. Just well, what we can do, I can do some. I'll set up the Hall effect sensors I've got. I can actually do some magnetic field measurements, and we can. God, it's going to have to be an expanded scale to do it. But what we could do is just see by putting signal through. We'll put signal through it and just see how much signal loss there is with cores and without. We'll just try it and see it as an experiment. Just see if they are lossy at the normal operational clocking frequency the things runs at, and also we'll see if it has any effect on decay rate on small target size. I don't know. This is what I say. This is why we experiment, and then we find out. And then we know it all, and we turn into a know-it-all. Yeah, anyway, that's an hour of coil stuff. But yeah, this is only to tell people, don't worry about your coils. Basically, for modified detector, if you crank up the gain and you crank up the frequency, and suddenly you go, oh, well, the detector is working so good, it's so quiet, you're in descents, don't continue detecting. You're not going to get any gold. You want your detector making a bit of burbly noise for sure. So always put a small target on the ground. Get yourself, who knows what, a bullet head, whatever, lead shot. Get some lead shot, eraldite it or hot melt glue it to a piece of wood or something you're not going to lose, something like that, and use that as a yardstick every time you go detecting. Throw it down, and if you detect it, great. And if you don't detect it, well, something's wrong. It's that simple, back off on the controls. You're pushing it too hard. You're doing burnouts down the street, and going nowhere fast, and making Bob Jane T-Marts rich. But yeah, see, there's a lot of things. It's a black art, isn't it? Oh, thank God that turns off by itself. Like I say, it's a black art to a degree, and we know certain things, and things are done differently than how we know they should work, by working in an optimum configuration, and they still work. Okay, still work. But yeah, like I say, we've got lots to play with. I've got too much to play with. Geez, I wish I could I wish I could clone myself or something, because it gets a bit ridiculous. Yeah. Okay, enough yabber. So yeah, oscilloscope wants to have a rest. It's been on all day. We'll kill that. And we'll kill this. And yeah, experiment, guys. Go nuts. Catch us.